Hi there, Christopher here, and I'm actually going to be starting a new series where I design a rocket around an existing postal tube that I got in the mail. So, when designing a high power rocket, you have to take a lot of considerations into fact, which is why you should probably plan it out in a design software like the one I have here, OpenRocket, before actually building it. So, the first thing that I did when looking at this was looking at my constraints and designing around that. So I first designed this tube right here, which I've now split into two tubes, which is going to be the main body tube made out of the postal tube that I got. From there, I went to the nose cone because that's going to provide a lot of my aerodynamics, and designed it to fit around the postal tube, and then played around with the dimensions until I got it right. From there, I looked at my other constraints, like the supplies I already have around me. For the motor mount, I'm going to be doing a 29mm motor by 14-inch motor mount. And so for that, I already have a fiberglass tube, so that was pretty easy to input into OpenRocket. This contrasts with the nose cone because the nose cone I'm going to be 3D printing, and PLA isn't currently in the materials database of OpenRocket, so I had to input it. So I had to figure out its density, dimensions, so on and so forth. From there, I went and looked at the centering rings. So the centering rings are going to be the main stabilizer of the motor mount and really holding the motor mount in the rocket itself. So for these, I'm going to be doing 1/4-inch plywood that I found that I'm going to laser cut. And so I input the dimensions that I needed, and I used 3 of them. So you usually want to use above 3 for motors like the motor that I'm going to be using, because those will provide the most stability while providing something for your fin tabs to grab onto. So from there, I had to design the fins, and this is where the main point, the first math comes in. And so I know what you're thinking: math, rocketry, rocket science, huge equations, so on and so forth. But this first one's actually not too bad. So for this first one, I was mainly looking at the aerodynamic stability that would be required and the fins that I would have to design to achieve that. So for this, OpenRocket actually calculates your stability in calipers, which contrasts with a MATLAB software that I've built, which calculates it in distance. So you might be asking, well, how do you measure stability? So stability in calipers is usually measured by taking the diameter of the rocket and measuring how many diameters of your rocket between your center of gravity and center of pressure there are. So in this case, I have 5.55 calipers of stability, which means that if I were to take the diameter of my rocket and make approximately 5.5 circles, I could line those up and fit them in between my center of pressure and center of gravity. Now, this is really important because the high power rockets I'm working with don't have thrust vectoring and rely on the aerodynamics of the rocket to remain stable. So for these, I just input my dimensions for the fin that looked okay and worked with the stability, and then I input my fin tabs. So for my rocket, I'm going to have the fins slot in through the main body tube and mount onto the motor tube. This will just provide a little bit more stability and also a little bit more grasping area for the fins. For calipers of stability, you're probably going to want to look at over 2 calipers is around the safe range. I actually might be pushing it into overstable with this rocket, and that is a condition where if there's a slight wind, the rocket will turn into the wind, which isn't too bad. It just means that you have to walk more for your rocket. From there, I had the main airframe designed, and I then had to look for motors. So OpenRocket actually has a whole motor database, and from there I just had to look at, okay, so this is going to be a 2.5 kilogram rocket with dry mass, and what motor to lift that. Now, 2.5 kilograms is a pretty hefty rocket for any of the motors that I'm going to be working with, so I'm probably going to want to work around the largest motor that I can find and reasonably fit in this rocket. which is going to be an I-204 motor. Now, I've actually flown this I-204 motor beforehand, and it has taken my other rocket, still testing Block 4, up to a mile up, which is quite impressive considering that at the time it was carrying a 100-gram payload. So, in this case, OpenRocket is saying it'll only carry it 509 meters, although I wouldn't trust OpenRocket because as you go into higher speeds, the equations kind of break down and you need to use other equations. So I actually have the numbers here, and when I input them into another software thrust curve, I got a maximum altitude of around 2,000 feet. Now this is a great contrast to the 5,000 feet that it takes my other rockets up, which just shows how heavy this rocket is. From there, while I was in the simulation software, I wanted to see some other things. So I wanted to also calculate my velocity at the end of the launch rod. Now this is important because the high power rockets, launch off of a rod, which keeps them stable up until the rod ends. So you want to be going fast enough by that point for the aerodynamic stability to kick in. So how I calculated this was I calculated the mass of the rocket, and then I calculated the thrust of the motor. Now this is where my equations kind of got weird. Normally you want a 5-to-1 thrust ratio, which will give you around 100 feet per second at the end of the rod. However, I was getting weird numbers like 15-to-1, which shouldn't be possible. So I actually sent it off to one of my buddies. He's going to be getting back to me on that one, and I will hopefully cover it in one of my other videos. Now, I was actually getting a maximum G-force also of 12.3 Gs. This is important because I'm going to be using a cardboard tube, and I don't want that to break because that would do a whole bunch of bad things for a rocket. 12.3 Gs is probably okay for this tube. It's definitely on the upper limit though. So from there, I had designed the rocket, figured out that it would be safe, and also figured out that it would probably look pretty cool. So I wanted to make sure that it would come back down safe though. So I had to calculate, with the current parachute size that I have, how fast would it come down. And this is where one of my MATLAB scripts came in. So I've actually coded a MATLAB splat calculator of sorts, where you could input the mass of the rocket, the size of the parachute, and the coefficient of drag of the parachute, and then it'll calculate how fast your rocket will hit the ground. Now, at the time of this recording, I have a 36-inch parachute, and when I input it into that, the rocket will be coming down at 18.9 miles per hour. Now, this may not seem like much, but it'll definitely do some damage to a cardboard tube. But one of the goals of this series was to make this high power rocket out of the only supplies that I have here. So I'm probably going to use that, and if the rocket has some weird cardboard crunching issues, then it'll just make for a better display. So that's the design finalized, and in the next video I will start building the motor mount.